Hello, welcome to another chemistry video. The objective of this one, after watching this video, you should be able to explain the significance of the experiments or models that each of the various scientists that we're going to study here, of what they did and how they were conducted. So today we'll talk about the quantum model, or quantum theory as it applies, well, really just to electrons. Quantum theory describes mathematically the wave properties of electrons and other very small particles. So today, subatomic particles, electrons. If you remember in the past, we had videos that discussed Einstein and other scientists and how there was a huge debate regarding light and whether or not light was a wave or light was a particle. And in the end, Einstein came up with this ideal that seemed to satisfy everyone, that light had wave-like properties as well as properties of a particle. Now, this also applies to electrons, we're going to find. Okay, enter Louis DeBroglie. He suggested that electrons were waves, not particles. He did a lot of math to prove this. Experiments he did, that electrons can be diffracted or their course bent, just like other waves. If you've ever been to a lake and there was a wall and there were waves hitting that wall, as they went around the end of the wall, if there was an end of the wall, the waves kind of bend around the end of it. Or perhaps you've seen, been in maybe a dark hallway and there was a lit room where the door was only open a little bit, or the edge of the door seemed to cast several shadows on the wall. Those are examples of light bending, and we already know that light has wave-like properties. So electrons are like this too. Also, scientists discovered that interference occurs when waves overlap. Now, this means that if perhaps the crest of one wave strikes the crest of another wave, we may have those waves doubling their energy. Or if the peak of one wave strikes at the trough or the lowest point on another wave, they may cancel each other out. Or it could be somewhere in between. Okay. So here I've got some links, which if they don't show up very well, I've got the hyperlinks. You can go and look at them yourself. Diffraction of waves, and this one, here's this example I was talking about. We've got some waves coming in from the left. They strike the edge of a wall, and you can see the waves kind of bend around the edge of that wall. Okay, this is called diffraction, around the edge of a slit in a wall. Okay, light does this, water does this, and electrons will do this. Okay, this second one, the resolution is absolutely horrible. So what we can do here, I can make this a little bit bigger so you can read it. If you go and you watch this YouTube video, it's actually a pretty good video. Let me make it just a little bigger. There, that should be easy enough for you to read. If you watch this YouTube video, it's an excellent explanation of quantum and electrons and how they act as a particle and as a wave at the same time when you have slits that the waves are traveling through, just as we just saw in this link right here. It's unfortunate I can't show it because it's a really good video. I recommend you go and check it out. Okay, moving on. The Heisenberg uncertainty principle. Perhaps you've watched the show Breaking Bad, and there's a gentleman in there, one of the actors, who says he's Heisenberg, and nobody ever really catches the humor unless they know who Heisenberg is and what the uncertainty principle is about. Well, as we've noticed before, that if in the Bohr model, we found that if light strikes an electron, in the form of a photon usually, it makes the electron change its position. It will jump to a higher energy level. So Heisenberg realized that the very act of looking at an electron requires us to shine some light on it. In other words, it's struck with some photons. So shining light on the electron is the same as hitting it with photons, or rather hitting it with some energy. This excites the electron and makes it move off course, usually to a higher orbital. A higher orbital and more energy means a different position and velocity. So the Heisenberg uncertainty principle, in a nutshell, It's impossible to determine at the same time both the position and velocity of an electron or any other tiny particle. The very act of looking at an electron changes its position and it changes its velocity. How weird is that? Well, welcome to the quantum world. The more certain of an electron's position, the less certain of the electron's velocity. And as I just said, just looking at an electron affects the position and velocity. Quantum has some really difficult to understand normalcies that don't fit in our world of big. Quantum's really small. Okay, so in an effort to try and understand this, we come along to Schrodinger. Schrodinger wave equation is it treated electrons as waves, and mathematically they showed that electrons are waves. He showed rather. Waves have specific energies and specific frequencies, as we've already shown. Okay, by combining the Heisenberg uncertainty principle with the outcomes from the Schrodinger equations, the probability of an electron's place around the nucleus could be determined. Not exactly where it is, but where it's probably at. So three-dimensional, an orbital, rather, is a three-dimensional region around the nucleus that indicates the probable location of an electron. And that's about it for this video. In our next video, we're going to talk more about these orbitals and the three-dimensional regions around the nucleus and where exactly we can find the electrons and how they're layered on top of each other and how they build on atoms as we move outward. Okay, well, thanks for watching. See you next time.